Good day, everyone. Welcome to lecture number 32 of this lecture series on computer organization and architecture. So, in this particular lecture, we will be discussing about the virtual memory. Okay, what is a virtual memory? Why is it required? And how we can implement this virtual memory technique. So basically, up to our last lecture, we have completed the discussion about the memory system, how caches can be used, how main memory can be used. But when we were discussing about the memory system, we were making two assumptions. The first assumption was assumption one. We were assuming that there is only one process in memory. But the reality is different. Reality is that there will be multiple processes in my memory. And because of having multiple processes in memory, there are some issues. The issues may be, for example, how we can avoid overlapping of these processes. Because we have to place multiple processes in the memory. So we should place those processes in such a way that they do not overlap with each other. Or we can say the address spaces of processes are not or we can say the address spaces of processes are not colliding. Okay, so what is the meaning of address space? Address space means the addresses accessed by a process, or we can say the addresses generated by a processes. So if we have multiple processes in the memory, the addresses generated by one process should be completely different from the addresses generated by the other process. And if we are able to maintain this, have this different address space of the processes, then we can avoid overlapping. Okay, so this is the first thing that we have to keep in mind, how we can avoid overlapping. The second thing that we have to keep in mind is that one process should not access the locations of other process. Okay, so this is a security issue. If one process can access the addresses, or we can say address the or access the memory locations that have been allocated to some process, then it can easily break the security of that process. Okay, so these are some of the issues that we have to handle. The second assumption that we are making is we were assuming that there is infinite main memory, or we can say whenever process requires some data, it will get that data from the main memory. Okay, we were assuming that everything is there in the main memory, but it is not always the case. The reality is we have finite main memory. So that means if I have main memory of 2 GB, let's suppose this is my main memory, and my process is of size 4 GB. How can I run a process of 4 GB on a 2 GB processor? Okay. So this is another issue that we have to take care of. So there are two issues. One is this overlap problem. and second is the size problem. We have to see how we can take care of overlap problem and how we can take care of size problem. As you can see, the overlap problem can be solved if I am able to have different address spaces for the processes. So if I have different address spaces for the processes, so that means they have their own address space, or we can say they have their own memory. They won't interfere with the memory that has been allocated to some other process. Okay, but we should know how we can provide different address spaces to the process. The other problem, size problem, how we can sort out this size problem, we have to take care of this as well. And to solve these two problems, overlap problem and size problem, so we are using the concept of virtual memory, or it is also called virtualization, or this is also called memory virtualization. And as I have said, that this virtual memory technique is used to overcome the overlap problem and the size problem. How it is doing, how memory virtualization is done, we will see its implementation. First, we have to understand the virtual memory, or we can say the memory virtualization. Then we will see how we can implement it in our processor. Implementation of virtual memory. Okay, so let's discuss it, how it is implemented. So first we will see what is virtual memory. Virtual memory is a concept, or we can say it is a hypothetical concept, where, not hypothetical, it is a concept where any process assumes that the entire addressable memory belongs to it. Okay, so in virtual memory or memory virtualization, process assumes that the entire addressable memory belongs to it, but in reality it is not the case. Okay, so what is the addressable memory? Addressable memory here means that a processor is generating, let's suppose, 32-bit addresses. Then using 32-bit addresses, how much memory we can address? So the total memory that is addressable is 2 raised power 32 bytes. That will be equal to 4 GB. So this is the total addressable memory. Okay, so this kind of memory, or this much memory, our processor can address, this much memory. But let's suppose we have only 2 GB of RAM. So our processor can address 4 GB memory, but we have only 2 GB of memory. So this is our addressable memory, and this is our physical memory. Okay, so that means in a virtual memory concept, process assumes that the entire addressable memory belongs to it. So our process, when we are creating a process, so that particular process will assume that it has 4 GB of memory. So when we are creating a process, so basically process is created by the operating system. So when an operating system creates a process, it creates a process. So it has a particular format for creating a process. What does that mean? It creates a process in this particular manner. So it will make a process like this, where it will assume that this process can occupy 4 GB of memory. Operating system is also saying that this process has how many memory? 4 GB of memory. As I said, that in virtual memory, process assumes that the entire addressable memory belongs to it, and here we are assuming that addressable memory is 4 GB. So it will lay down this process in this particular manner, where at the bottom it will divide it into different sections. We have header. Header contains the information about the process, for example, the size of process, the permissions associated with the process, for example, whether this process can be run by different users or not. Then another section is the text section. This text section contains this particular section contains the code, or we can say the instructions of the process. Then we have the data section. This data section will contain the initialized, or we can say statically initialized data. Then we have another section. This is also called BSS section. This particular section contains the uninitialized data. Okay. Then we have another section which is the heap, and then at the top we have the stack. We can say that operating system has created a process, and it has created a process in such a way that it is saying that it has this entire 4 GB memory. This is from 0 to 4 GB. Or we can say this address is 0 and the top address is 2 raised power 32 minus 1. This is the top address. But you have to keep in mind, this is the virtual memory of a process. Okay, or this is also called virtual memory map of a process. Fine. Now there is one thing that this, as I said, that this is the way a processor, or we can say operating system, lays down a process into memory. I won't go deep into this because some portion is also reserved here for the operating system itself. So let's suppose only 3 GB, up to 3 GB we have the memory, virtual memory for the process. The remaining 1 GB is for the operating system, but we won't be discussing that in detail. It is out of the scope of this particular course. So you can go and take the operating system course to learn more about this. And for this entire different sections of the process in memory, you can watch a video whose link has been given in the description section. Okay. So this is how we are creating the virtual map of a process. Now basically we have to place this particular process, or this virtual map of a process, into physical memory. This is only one process. There may be hundreds of such processes. So every process, let's suppose it has how many virtual memory? 4 GB. Let's suppose I have 10 such processes. So how many virtual memory? 40 GB. Now my actual physical memory is only 2 GB. How can I place this 40 GB into this 2 GB? Because I am running 10 processes at a time. So how will I do it? I will not place, so let me write it here. So what I am saying, that we have virtual memory of process 1, we have virtual memory of process 2, we have virtual memory of process 3, and so on, virtual memory of process 10. This process 1 assumes that all the addresses from 0 to 2 raised power 32 minus 1 belongs to it. It also assumes the same, it also assumes the same, and this one also assumes the same. But we have to place these virtual memories of a process into a physical memory. Can we place this entire virtual memory of these processes into a limited physical memory? No, it is not possible. So what can we do is that some portion of P1, some portion of P2, some portion of P3 dash 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 P10 will be placed in physical memory. And the other portion, this portion is from their virtual memory. Okay, some portion of their virtual memory is placed in the physical memory and other portion is placed in the secondary memory. So if some process requires some data, or we can say it wants to access some portion of its virtual memory, and if that portion is there in the physical memory, it will get that into the physical memory. However, if that portion is not into the physical memory, it is in the secondary memory. Okay, so in that particular case we will say miss. Then in that particular scenario, it has to go to the secondary memory, get that portion from the secondary memory into the physical memory, and then use it. Okay, this is how we can implement the virtual memory using the physical memory. Now, as we have said that process P1 has its own address space, so it has its own address space from 0 to 2 raised power 32 minus 1. It has its own address space, it has its own address space, it has its own address space. If process P1 is generating an address like this, for example, it is generating address 35. So this particular address will be its virtual address, because it is assuming that its addresses are from 0 to 2 raised power 32 minus 1, and it is generating a address 35. It is saying that I need a data, or we can say some instruction which is stored at virtual address 35. But basically this P1 has been mapped into the physical memory. So that means this 35, this address will be somewhere in the physical memory. Let's suppose the address of this wire, this particular portion is mapped, address is 20. Okay, so if P1 is saying I require data at address 35, which is the virtual address, we have to find its mapped location in physical memory, because we have mapped this this virtual memory into physical memory. So let's suppose the location 35 is stored at location 20 in physical memory. Okay, so when process P1 generates address, which address? 35. We have to convert this address into 20, and then we will access physical memory and get data, and then return that data back to the process. So that means we require some kind of mechanism here that converts virtual addresses to physical addresses. Okay, and this particular hardware is called a memory management unit. We will see how it is doing this, how it is converting a virtual address into physical address, but you should understand why we have to convert virtual address to physical address. We have to convert virtual address to physical address because we are mapping the virtual memory of process into the physical memory. Okay. Fine. Now let's see how this virtualization is able to solve our problems. So what were our problems? So let me write the problems. So the first problem was overlap problem. So let's see how it is able to solve this overlap problem. Virtual memory. So let's consider only two processes, P1 and P2. Okay. When we are creating a process P1 and P2, or I can say when operating system is creating a process P1 and P2, it is creating virtual memory map of P1. It is saying that its addresses is from 0 to 2 raised power 32 minus 1. And it is also creating virtual map of P2. It is also 0 to 2 raised power 32 minus 1. Okay, now as we know, let's suppose our memory, this physical memory is only some, let's say it is only 2 GB. Okay, what we are going to do, we will take some portion of virtual memory of P1 and place it here. So let's suppose P1 is placed here. So this is it is physical memory. So it is some portion is placed in this physical memory, and here we are placing P2, let's suppose. Okay, and the remaining portion is placed in secondary storage. So now let's suppose P1, and we will P1. So first we are doing, when we are taking some portion of P1, we can place it anywhere. Whatever is the free, we will place it there. Let's suppose P1 generates an address 35. It is a virtual address. So we will have a memory management unit. It will see that this address is generated by P1. Then it will use something. So we will determine the procedure. It will use some procedure or some mechanism to convert this 35, which is the virtual address of P1, into physical address of P1, where this 35 has been placed, and it will give us the physical address, and then we will access the memory. So this memory management unit will make it possible that one process will not access the physical memory of the other process. So it will convert these virtual addresses to only those physical addresses which have been given to P1. It won't generate those addresses which have been given to P2. Okay, so now using this particular technique, we can overcome the overlap problem. Okay, when we discuss how we are actually implementing it, there I will make it clear, but you should understand how it is doing. Now the second is size problem. So as you can see, for example, our physical memory was only how many, what was the size? 2 GB. But even processes of size larger than 2 GB, for example 4 GB, using this memory virtualization, we can even run 4 GB processes on a 2 GB memory. Even if I have 10 such processes, I can run 10 such processes onto a 2 GB memory by using a concept of memory virtualization. Okay, fine. So this was what is memory virtualization. So let me repeat it. So in memory virtualization, or we can say virtual memory, processes assume that the entire addressable memory belongs to one process, belongs to a process, belongs to itself. Okay, this addressable memory is basically the virtual addressable memory. And you have to remember the address is generated by a process. In this particular technique, in virtual memory, the address is generated by a process, or we can say the address is generated by a processor, are all virtual addresses. And we have to convert those virtual addresses into physical addresses. Okay. So when we are saying that every process, let's suppose we have a process P1, it has its virtual memory. This is its virtual memory. Process P2, it has its own virtual memory. Likewise, other processes. But we have only one physical memory. Now what we are doing, we are mapping some portion of P1 into physical memory and some portion of P2 and other process also into the physical memory mapping. And the remaining portion is the remaining portion of P1, P2 of virtual memory. It is placed in the secondary storage. Okay. So if P1 requires some data, so that means it, let's suppose it requires some data in its virtual memory at this location. Now, as I said, some portion from its virtual memory has been placed in the physical memory. If this portion has been placed in the physical memory, it will say that I requires this data in virtual memory, and we will convert this into the location in the physical memory using memory management unit. And if this location is there in the physical memory, we will get that location, get that data in the physical memory. However, if that data is not in the physical memory, then it will be in the secondary storage. We will get that data from the secondary storage and then use it. Now our aim is to discuss how we can map some portion from their virtual memories into the physical memories. Okay, so that is the main discussion. The discussion is how to implement virtual memory. And for implementing virtual memory or memory virtualization, we will discuss three things. The first, we will discuss the option one, or we can say the solution one. We have three solutions: option one, option two, and option three. This option one we will discuss first, then in option two we will discuss segmentation, and in option three we will discuss paging. So these three options are the mechanisms to implement virtual memory. Okay, so let's first see option one. Fine, then we will see what is the disadvantage of option one, and likewise we will move forward. So let's first discuss the option one. Okay, in option one, let's say we have process P1 whose virtual memory is like this, and we have process P2 whose virtual memory is like this. So we will divide this process, its virtual memory, into words, or we can say bytes. Let's only use words. Okay, so this is word 0 of P1, this is word 1, word 2, word 3, word 4, dash dash dash, and these are the words of P2. But you should understand that these are the virtual words. Word 0 of P2, word 1, word 2. So when I am writing W0, it means the address, virtual address. Virtual address of W0 means of location 0. And at this location, let's suppose I have some data stored, D1. At word 1, I have data stored D2. At word 2, I have data stored D3. Okay. Likewise in P1, let's suppose at word 0 I have data stored B1. Word 1 data stored is B2. Word 2 data stored is B3. Okay. Now I have to place some words from P1 and some words from P2 into the main memory. So what we are doing, we have the main memory. We will divide this main memory also into words. Okay, and let's name this is P0. This is sorry, let me use some other notation. The other notation, let's suppose this is address 0, this is address 1, this is address 2. But you should understand that A0 is the physical address, actual address. This W0, W1, these are virtual addresses. Okay, A0, A1, A2, A3 and A4, let's say. Now what I have to do, I have to place some words from P1, some words from P2, some words from P3. So these are virtual words into the main memory. So let's say I am placing word 2, or we can say the data of word 2 of P1 here at address 0. At address 1, I am placing D2. At address 2, I am placing D3. At address 3, I am placing B1. Let's say. So for example, let's say I have placed these data items into the physical memory. Where will I place the remaining items? The remaining items will be placed in the secondary memory. Okay. Now let's say, for example, P1 wants a data stored at address W0. So P1 requires a data stored at address W0. W0 is the virtual address of P1. Where have we placed W0? The data of W0 B1. We have placed at A3. Okay, but we should know where we are placing these data. So here I am simply saying I will place B1 at A3, B2 at some other location into the secondary memory, but we should have some mapping also which will tell me where I am placing this word, where I am placing this address, the data of this address. Okay, so for that particular purpose we have a mapping table. Mapping table. Mapping table stores the information. What information? Mapping information. Mapping information means it will say where we are placing the data items. Okay, so what I mean to say, for example, it will say that let me write in this particular manner. We can say, let's suppose we have a mapping table per process. Every process has its own mapping table. So let's say this is the mapping table of P1. And this mapping table will be indexed by the virtual address. For example, this will be W0, virtual address 0. Okay. It will say where this W0 is placed in the main memory. So where have we placed the data of W0? At address A3. So it will store the address A3. So this is the virtual address and this is the physical address where it has been placed in the main memory. Likewise, if we have W1, where is W1 placed? B2. Is there anywhere in here? No. Okay, so it is not placed anywhere. So we will add another information here. From this part, we say is valid. Valid means that yes, this particular word has been mapped into the main memory. Invalid means, so valid, if valid is 1 means yes, this word is there in the main memory. If this bit is 0 means no. this word is not in the main memory. So that means this word is into the secondary memory. Fine. So likewise, I will have this table. And how many entries will be in this particular table? It will be number of words in this virtual memory. Okay. So this is mapping table for P1. Likewise, we will have another mapping table for P2. Now let's see if P1 requires a data W0. So this W0 is virtual address. And for this virtual address, it should get the physical address. So we will have a memory management unit. It will check the mapping table of P1. So it will go here. It will see W0 address. It will go at W0 location and it will see whether this particular word is placed in the main memory or not. So here you can see, yes, it is placed in the main memory. And it will return A3. A3 means that this particular word is stored in the physical memory at address A3. So it will access that address and it will get the data item. However, if the word is not present, so that means it is not present in the main memory. Okay, this is called a main memory hit, and in that scenario it will be a miss, and in the miss scenario it has to go to the secondary memory and get that word into the primary memory. Okay, so this is option 1. Here it is a simple option, but similar options are there and I will go in detail for other options, but this is very simple how we are implementing virtual memory. But the main disadvantage of this particular approach is this mapping table. So this mapping table will be very huge. It will be having a large size, very huge size. And we have to store the mapping table into the main memory. And if we have 10 processes, then every process will be having its own mapping table, and placing all those mapping tables into the main memory will add a extra storage overhead. Okay, so that is the disadvantage of this option. Okay, fine, this is option 1. So let me repeat it. So in option 1, what we are doing, we are placing virtual words of processes into the main memory words. This is the first thing, and storing the mapping information into per process mapping table. Okay, the words which are not in main memory will be in the secondary memory. This is how we are doing. Now, during accessing, if I want to access some data, so the process, some process sends its virtual address of a word to a memory management unit. This memory management unit, what it is going to do first, it will access the mapping table of process. Let's suppose this is process P1. So now after accessing the mapping table of process P1, it will see its location, this location, virtual address, or from this it will get what is the physical address related to this virtual address. If this physical address related to this virtual address is, so there are two parts. It is valid, another is it is invalid. Valid means that physical address is present. So that means this particular word is present in the main memory. So it will return data present at physical address. Okay. However, if that entry is invalid means this is also called hit. Invalid means this particular word, virtual word, has not been placed in the main memory. So then it has to access secondary storage. Access secondary storage means get that virtual word into physical memory and update the mapping table. Okay, so this is how option 1 implements virtual memory. But as I said, the limitation is the large size of mapping tables. Okay, so that is why we are moving to option 2 and option 3. So basically you will see that option 3, the paging option, as I said that there are 3 options for implementing virtual memory. Option 1 we discussed, option 2 is segmentation and paging. This option 1 and option 3 are similar, but the only change is that in paging we decrease the size of page tables that are used in option 1. How we are doing that, what is paging, we will discuss it, but they are very related to each other. Okay, first let me discuss option 2, then we will see what is the disadvantage of option 2, then we will move to option 3. Okay, so we will stop this particular video here, this video lecture, and in the next lecture we will start with the segmentation. What is segmentation and what is paging? Okay, or we can say how segmentation and paging can be used to implement virtual memory. So let's meet in the next lecture. Till then, goodbye.